Kirchhoff's current law is another fundamental law of circuit analysis. It states that the algebraic sum of the currents connected to a node must equal 0. To verify this law, we choose a simple circuit consisting of a DC battery, a resistor R1, a resistor R2, and a resistor R3. Naturally, there are 3 branches in this circuit. Label the branch currents as I1, I2, and I3. Here, the point where the 3 branches meet is called node A, located at the top section. We want to apply KCL here. According to KCL, the current entering the node, which here is I1, must equal the sum of the currents leaving the node. One of each is I2 flowing through resistor R2 and the other is I3. Therefore, I1 equals to I2 plus I3. This is the result of KCL at node A. We now want to verify this practically. However, we can first take our analysis a bit further. Here, R2 and R3 are in parallel. So R2 and R3 will form a single equivalent resistant, which we call R. When we substitute R in place of R2 and R3, R and R1 are in series. The DC battery must supply current through this series combination. Therefore, by substituting R equals to R2 parallel R3, we arrive at the result that current I1 produced by the source equals VDC divided by R1 plus R. Now, we have I1. If we return the circuit to its original configuration, we can express I2 and I3 using current division. Since R2 was in parallel with R3, the current flowing through R2 equals the other parallel resistor, here R3, divided by the sum R2 plus R3 multiplied by the total current we calculated as I1. So I2 equals R3 times I1 divided by sum of the R2 and R3. And we can perform the same calculation for I3. Now we want to verify these theoretically calculated values with measurement. We choose VDC equals to 20 volts, R1 1K, R2 2.2K, and R3 3.3K. We now draw a table. With our VDC at 20 volts, we obtain I1 according to the relationship. First, we compute R2 parallel R3 equals to 1.32K. Substituting to I1 relation, mark it here, we earn I1 as 8.62 milli. Okay. Now for I2, we use this equation and we obtain our I2 as 5.17 milliampere. And IC can also be easily obtained from this relation. equals 3.45 milliampere. Now, these results obtained theoretically must be verified against the practical circuit. To measure I1, the multimeter must be set to current measuring mode and connected in series with the 1K resistor. Since two components in series naturally carry equal currents, I1 is measured this way. After measuring I1, we should remove the multimeter from that section and return the circuit to its original configuration. Now we connect the multimeter in series with the 2.2K resistor to measure I2 and do the same for I3 as well. We want to verify KCL in this circuit. Together we will measure the currents and confirm the validity of the law and truly understand it. Here we have a DC battery whose positive terminal is connected to node A and the negative terminal to node G. The positive end is the red wire and the negative end is the blue wire. The battery value is 20 volts. This column is node A. R1 is between node A and the next node, node B. From node B to node G, two resistors R2 and R3 are placed in parallel. Well, according to KCL, the current I1 that enters node B through resistor R1 must return to node G through I2 and I3. Therefore, I1 equals I2 plus I3. So we need to measure I1, I2 and I3 and confirm the validity of the KCL. Let's check it. First, let's measure the battery voltage. Since our battery is a 20 volts DC source, let's see if the battery value, yes, is indeed 20 volts. Now let's set the multimeter to current measurement mode. So we configure it by placing the positive port into the milliamp range. We want to measure the current through resistor R1, that is I1. For this, we disconnect one leg of the resistor and place it in a new location. Notice I'm disconnecting this resistor leg from this side, the column connected to the battery, and place it in a new column. Now, if I set the multimeter to milliamp mode and set its port as well to current measurement, I can connect the multimeter across these two ends. It becomes in series with the component and the current is measured. In this case, 8.68 milliampere was the current through resistor R1, that is I1, was measured. So I need to return R1 to its previous location so the circuit stays connect and function properly, and move on to resistor R2 to measure I2. I can disconnect this leg from node B and connect it to a new column. For example, this column. From this column, which now becomes the new one, essentially the previous node B, the multimeter must connect these two and thereby becomes in series with R2. So I place the multimeter and at the new node, let's call it B prime, connected to the same node at B. We can see here that a negative current sign appeared, minus 5 5.25. The magnitude is correct. The negative sign is because we swipe it, the multimeter's positive and negative leads. That is, the positive and negative were reversed. If I swap, you will see that the sign becomes positive, 5.25 milliamps. So the current through resistor R2, that is I2, equals 5.25 milliamps. I return R2 to its previous location, that is back to node B. Now let's move on the resistor R3 and measure I3. Now I can again disconnect this leg just to show you it doesn't matter which leg, and place it into the new column. And then I proceed to measure the current value. So I place the multimeter between the new column and the previous one. The current, as you can observe, is 3.42 milliamps this time. So I1, I2, and I3 have been measured, and now we can check KCL together. So, as you can observe, the agreements between the results are found to be good. Again, there is a slight difference in measurement results with the other results, mainly due to the tolerance of the resistors. I hope you enjoyed this video.